They're in. So I'd like to thank the organizers for inviting me and remembering that they invited me. And well, I see here already, I just like my checks. I put the wrong year at the beginning of the new year. Okay, so here's the title of the talk, and this is joint work with Franco Saliola and Ben Steinberg. And this is a summary of work we've done for about the last 10 or 15 years. Okay, so we're going to study various combinatorial objects by assigning algebraic invariance to them. This is maybe the definition of algebraic combinatorics. What might be unique here or new to people here is that I'm going to use a semigroup rather strongly. And so I come from semigroup theory. So when I look at this picture, I see a semigroup with 13 elements. So where is it? Okay. Now I think most people in algebraic combinatorics will see a hyperplane arrangement with 3 lines in R2 or the Coxeter complex at S3. So where is the semigroup? Well, where are the 13 elements? Okay. Well, I'm going to look at the faces of this hyperplane arrangement. There's one of dimension 0. There are the 6 rays of dimension 1 and the 6 chambers of dimension 2, and there are 13 elements. Okay. So I have 13 elements, and now I'm going to define the product. So the modeling structure on this arrangement, or any hyperplane arrangement, is defined this way. It's a product on the set of all faces. So here's a red face X and a blue face Y. And geometrically, I walk a little bit from X towards Y, and the first face I fall into is the product X, Y. So we see that this product, a couple of things about this product. It's not commutative. If I look at YX, it would be this face over here. Okay. It's not too hard to check that it's associative, so there's a semigroup. It's not too hard to check that the origin acts as the identity element. But it's about as far away from a group as you can possibly be, because if you take this definition and you apply X to itself, X squared is equal to X. Every element is an eigengroup. Okay. So it's sort of on the other side of the world from groups. Okay, so here's another way of looking at, I should say that this product was defined originally by Tietz, but he looked at it as a geometer should as a projection of one face on another. So he would call this the projection of Y on X. And you looked at it as a unary operator. And as a unary operator, he wrote down some rules.
What's the product of the triangle and the edge is always a triangle?
Yes.
And the product of 2 triangles
is always the first triangle.
Always also.
It's basically about convexity.
So the outcome always never ends.
Except for an edge with itself. In the 2-dimensional case. Okay, so he didn't notice it. He wrote down a rule about projections, but didn't look at it as a binary operation. So if you look this was a foundation in the theory of building. If you look in Ken Brown's book, the first version of theory of building, the semigroup does not appear. In the second version, it appears on page 29 and is used extensively. So once it was noticed that it was that there was a semigroup product here, the semigroup became important, and that's what I'm going to try to talk about today. Well, here's another way to define the semigroup. Well, in incident geometry or incident systems is a binary idea. Right? In an incident system, you have a set of points and a set of blocks, and a point is either on a block or not on a block. here, but in real geometry, there's a sort of ternary choice. So look at the dark line going diagonally. Well, you could be on the plus side of that line, you could be on the line, or you could be on the minus side of the line, where you choose plus and minus arbitrarily. Okay? So I can tell you, I can give a name to that sector by saying, okay, I've decided with the 3 lines, this is the plus side of all 3 lines. And this is what we do, in fact, when we learn early about the planar axes. The first quadrant is plus plus, the second quadrant is minus plus, and it's actually a generalization. Okay, so now I'm going to walk around. I walk to this line, and the 0 in the first position now says I am on the first line, but still on the positive side of the other 2 lines. And now I'm going to walk around. Now I'm on the negative side of the first line, and still on the plus side of the other 2 lines, etc. Now I get to stop once instead of going counterclockwise here, and somebody pointed out I'm actually going clockwise. I said in Hebrew would be right to left, and our clocks go the other way too. Okay. Okay, so now I've labeled all of it. I have 13 labeled signs. And what one notices is that the product, the geometric product I gave before, is now multiplying in a certain 3-element monoid, generalizing the 2-element Boolean monoid 0 and 1, in which 0 is the identity element and plus and minus absorb on the left. So plus times plus is plus times minus is plus, and minus minus is minus plus is minus. So these are left zeros. So x in the previous slide geometrically was 0 minus minus. Y is plus 0 plus. Okay. Now I multiply. 0 times plus is plus. Minus times 0 is minus. Minus times plus is minus. I get plus minus minus, and that's the sector that I end up in. Okay, so it's not obvious that that's what's going on, but it's not a hard exercise. So here's an algebraic determination of the product that I defined geometrically previously. Okay, so I want to understand this product. And if people are familiar with things like oriented matroids, these sign covectors, as they are called, play an important role in the theory. In fact, oriented matroids are defined as a collection of these signs closed under multiplication plus another axiom, which I'll maybe talk about later. Okay, so now I want to look at these semigroups. So this is the name of the class of semigroup that this semigroup belongs to. It's not a very useful name. Left might make sense because of that left theorem, but regular is an overused word. Schützenberger actually defined these in 1947, and he called them skew lattices, which is a better name, but unfortunately we're stuck with this. So I look at the semigroup, and here are 2 laws that define it. They're not motivated except to check that you can check easily that this semigroup satisfies this property. If I move from X to Y and then try to move back to X by convexity, I can't move, I stay in the same place. So X times Y is plus minus minus. Now if I try to move back to X, well, I'm convex. If I move a little in that space, I stay where I am. So X times Y times X is XY. Maybe too hard to see specifically. But here's going to be a slide. So here I'm going to give a collection of equivalent conditions to this law. B is a band. Band is the name for a semigroup. All of those elements are idempotent. Sets under intersection, for example. This says essentially that repetitions are erased. If I see X, if I do X and I do Y and I do X again, I can cancel the second X. That's what this rule means as I read from left to right. And so here's the conditions. Okay. So the conditions are, if I have a semigroup consisting only of idempotents, it satisfies these 2 laws if and only if this relation x less than or equal to y if and only if the principal right ideal, semigroups have ideals, right ideals, left ideals, ideals, like groups, but more like rings, is a partial order. Okay, so let's take a group, non-trivial group. What's a right ideal in a group? Why didn't you learn about that in algebra? Well, right ideal, you can start with an element x in a group, multiply on the right, and get to any other element. So there's only one ideal and right ideal in a group. It's the whole group. So the relationship x less than y in a group, if I have containment of right ideals, is the universal relation. Here, this relationship is a partial order, which means that I can consider a left regular band also as a partially ordered set. Just means that being a partial order just means that every principal right ideal has a unique generator. Now, not only does it have a unique generator, not only can we consider B as a partially ordered set, but with the connection to the multiplication is that left multiplication preserves this equality. So we have already built into the foundations a partially ordered set and a left multiplication which preserves the order. Okay? And if you have a post set, well, a post set is the same thing as a simplicial complex. Every post set, we have a simplicial complex of its chains. Every simplicial complex, we have a post set. We use natural order on the face. Although it's clear that this multiplication on this partial order extends to chains in this partially ordered set, and so we have naturally already an action of this monoid on a simplicial complex, and not only a simplicial complex, now let's assume there's an identity element. The simplicial complex is contractible. The identity element can be added to any chain. The identity element is its right ideal that it generates is the whole monoid, so it's above everything, it's a maximal element. And by basic facts about simplicial complex, it means the identity is a phone point and this simplicial complex is contractible. Well, this is almost the whole talk because a left regular band automatically acts on a contractible space. You're going to know a lot about the underlying homology and topology of the space. And now you just try to turn the crank in the right direction. Okay, well, we're going to look at, so the talk is going to give some basic facts, then lots of examples, and then some deeper facts. So I want to study the representation theory of these monoids. So what's representation theory? Linear representation theory. I'm going to represent the monoid by matrices over some field. Generalizing group representation theory. And then I want to know the usual kind of questions that people would ask in the theory of algebra. So now the fact is that if I look at the collection of principal left ideals, and here in monoids, left is different from right. Right in group theory, right multiplications are essentially the same as left multiplications, so we have inversion. Here the key is that left multiplications and right multiplications are different, and you have to understand how they're connected. So it's a fact, not obvious, but it's a fact that the intersection of two principal left ideals is another one. And not only another one, it's the principal left ideal generated by the product. And that's a theorem, special case of the theorem of A.H. Clifford from 1940. But here we interpret it this way. It just means that I can consider the collection of principal left ideals as a lattice or semi-lattice under intersection. That's what that says. And that B, this fact, just says the assigning of the element B in the left regular band to its principal left ideal, it's a homomorphism model. And this is sort of commutification. This is sort of like commutative. This lambda B is in fact the maximal commutative image of this left regular band. These are facts that are not obvious from a short talk, but part of the basic facts about symmetries. Now, what's wonderful here is if K is a field, I have this homomorphism. I can extend it in the obvious way from the algebra of the monoid. So just like there's a group algebra, there's a monoid algebra, formal linear combinations of elements of B. And we can map this B to lambda B extends from the algebra of B to the algebra of lambda B. And it turns out that the kernel of this morphism is exactly the Jacobson radical. Okay, well, that's very special. And so I sort of have the Jacobson radical of the algebra I want to study. And of course, in group theory, if we're doing, say, characteristic 0, there is no Jacobson radical, right? Group algebras over a field with good characteristics are semi-simple, but here, these algebras are not commutative or never semi-simple. So I have to understand the radical. What's lucky for us is that it's fairly easy to understand. I can utilize and take the kernel and the map. It's not so hard. An old theorem of Lewis Solomon says that if we have a commutative idempotent semigroup, it's algebra semi-simple. It's basically Mobius inversion. So the theorem of inclusion exclusion basically can be interpreted algebraically as saying that the algebra, the collection of subsets under intersection, is a semi-simple algebra. That's a fantastic connection. There's lots of nice generalization. Okay, so by general facts, this tells me that if I want to know what the simple modules of this algebra are, they're the same as the simple algebras, its maximal semi-simple image. And all these guys have, here, we'll see in a moment, have dimension 1. So the simple modules of a left regular band algebra are indexed by a lattice, namely this lattice. So that's already not, you see that there's these two little equations which define left regular bands lead to a lot of nice information. And so we have a complete understanding of what the semi-simple image is. The algebra modulo is radical, but that's the algebra modulo this kernel we talked about. It's the algebra by the first isomorphism theorem. It's the algebra of this lattice of principal left ideals. And by the theorem of Solomon, that splits into a direct sum of K lambda B times, or by whatever it's commutative and it's semi-simple. And then you can write down the characters of the simple modules. They're basically filters. I stand at an element in the lattice. I take an element A in the monoid, I map to the lattice. If it's greater or equal to this element X, I say 1, and if it's not, I say 0. Those are filters so basically filters in the lattice lifted back via this morphism sigma to the monoid. Those give me all the simple characters of the monoid. Okay, so K of B is a basic algebra. It means that all the simple modules are one-dimensional, or that KB has a faithful representation by triangular matrices. These are basic facts about basic algebras. And this is just, if you don't remember, just like a brief idea why basic algebras are important. That just means that the semi-simple algebra is a direct sum of field. The simple modules are one-dimensional. And why is basic algebra important? Every algebra is Morita equivalent to unique basic algebra. Morita equivalent means the category of modules over the algebras are the same. Well, I might as well choose something easy to understand. So I can replace any algebra by a basic algebra. And here in the case of left regular bands, I have a really concrete version of what this basic algebra associated, what it is. Well, the algebra itself is basic. Okay, now here's the connection to, now I'm going to talk about why this is nice for conference on algebraic combinatorics. Lots of combinatorial structures have been shown to have the structure of a left regular band. Well, I showed you the idea for real hyperplane arrangements, and this goes back to Tietz and to these Bidiger, Hanlon, and Rockmore, who wrote a fundamental paper in 1995. Oriented matroids, if you want to know what they are. Well, oriented matroids are a bunch of these plus zero minuses closed under the multiplication I gave and satisfying one extra axiom, which said basically that there's a hyperplane separating any two points. They're not on the hyperplane. Just like there is in a hyperplane arrangement, there's exactly one line that you move over in different supposition. That's an oriented matroid, one of the definitions. Matroids themselves have the structure of a left regular band. So the basic matroid would be, say, independent columns in a matrix. I can concatenate two matrices and strike out new dependencies. That gives me a product. Show that product as a left regular band. So Ken Brown decided to define that left regular band. There's a notion of a hyperplane arrangement. Of course, there's a notion of complex hyperplane arrangements. Bjorner gave a definition, showed how they can be considered to be left regular bands. Something called greedoid. Greedoid is a generalization of a matroid that comes up in studying greedy algorithms. So the difference is that a greedoid has an exchange property, but it need not be a superficial complex. So there could be a subset of a phase which is not a phase, but they still have some kind of exchange property. And there is a generalization complex of oriented matroids, which more or less includes most of the previous examples. And this was defined by Vandel, Chapoy, and Knauer in 2015. And so there are lots of generalizations, basically by taking the axioms for oriented matroids, and there are various choices that come up from applied problems that give you a more general class. These COMs are the most general. Well, just like in group theory, random Markov chains can be analyzed via LRD representation theory. Random Markov chains can be modeled as random walks on these models. Just like many random walks of groups are important. And this has been done by a good number of mathematicians. So now let me give you an example. Because he says, I've given this example every talk I ever gave to Corey-Lan, and finally wrote a paper about it. So it was successful. Okay, so the free left regular band. It has a nice combinatorial structure. The law says that I can erase repeats. So, well, the free monoid is just a bunch of words over and after that. But now if I read the word left to right, that rule xyx equals xy says the second time I see any letter, I can erase it. So I can always reduce a word to a repetition-free word. Every letter appears at most once as I read left to right. And it's not too hard to show. That's a normal form for the free left regular band. Right? Algebra is defined by identities at free objects. Okay. And then here's the multiplication. We concatenate two free repetition-free words and strike out any new repetitions we make. So if I have 1, 4, 5, 3, 2, if I multiply by 3, well now 3 is seen twice, but I read left to right, so I strike out the second 3. That's the product in the free left regular band. This model Markov chain that had been looked at earlier and not noticed to be a random walk on the on this monoid. So think of these as 1, 2, 3, 4, 5 is a set of books, and I want to pick a book to take out. When I bring it back, I put it in front of the pile. I'm a librarian and I'm lazy. I want to give the books that are closest to me. So when a book comes back, I assume it's popular. I put it next to it. Well, that's exactly this multiplication. And by iterating this, you get a random walk on the set of books. Okay. So that's more or less what I just said. And then this has been studied before, but then you have this paper by Bittergier, Hadwin, and Rockmore use the representation theory of left regular bands to get the kind of things that you want to know about when you're studying Markov chains. And Brown and Diaconis generalized this and proved a lot more. So I won't get into the details of the random walk theory. Those of you familiar with random walks can see that this is a nice thing to do, and you get very nice kind of answers. And then Brown noticed that what he did in the case of they were using hyperplane arrangement monoids could be generalized to all left regular band monoids. So left regular bands are very geometric and very amenable to understanding their long-term behavior in terms of random walks. So other people who work in this direction. So now I'm going to give another example. So we have the free left regular band. Now I'm going to talk about partially commutative left regular band. So this is a generalization. If this was a talking group theory, I'd be talking about right angle arcing groups. If I'm talking about monoids in communicating processes, I'd be talking about quantum monoids or partially commutative monoids. I'm going to define these in the land of left regular bands. So we have a free partial commutative left regular band. Well, let's start with the free left regular band and take our relations relative to that. So I already have repetition-free words. I have a graph, let's say a simple graph, and the graph just tells me which letters commute. And so this is a familiar kind of object in various parts of the number. So that's the graph, the left regular band. FG is take words, repetition-free words, use a graph to tell you which letters commute, and now tell me what this monoid looks like. Well, so examples, if I don't have any relations, if the graph is empty, there are no edges, then I just get the free left regular band. I don't have no letters commute. If I have the complete graph, all letters commute. Okay, so if I have, that means any two words written on the same alphabet are the same, because I can commute all letters. Well, that just means I have to tell you, given a word, what are the set of letters in? And that gives me the solution to the word problem. Well, that's just sets of subsets of the edges of the graph, of the vertices of the graph under union. So here we have, on one side, we have a full free commutative left regular band that is subsets under union. On the other side, we have a free left regular band, no commutation, everybody else is in between. So this I've mentioned, these are in semigroup theory and monoid theory, they come up in looking at communicating processes. In group theory, they're right angle arcing groups. And now I'm going to give you a solution to the word problem, which is kind of nice. So here's an example. G is this graph. So the graph tells me that A and D commute, C and B commute, etc. But A and C and B and D don't commute. So G is the graph that tells me, this is a choice in the beginning, some authors do it the other way, but I'm doing it this way. G tells me which letters commute, and G bar, the complementary graph, tells me what letters don't commute. Okay. Then you can prove that the word problem, the set of elements of this free partial commutative left regular band are exactly in one-to-one correspondence with acyclic orientations on subgraphs, induced subgraphs of the vertices. So let's say I'm interested in A, B, and C, given those are the commutations. Well, I know A and D commute, and I know D and C commute, but I don't know anything about C and A. Well, there are two choices. C comes before A, or A comes before C. So this acyclic orientation corresponds to these three elements, C, A, D. I can push D in the middle or to the left. It commutes with both C and A. So I have three elements equal to it in this free partially commutative LRB. And then the theorem is that that's exactly the set of elements equal to CAD or CAD, CDA, DCA, and you can see the connection to the acyclic orientation on this graph. So it's a beautiful idea that has a nice combinatorial solution for the model. Okay, and then what happens if I start multiplying using the left regular multiplication? So here I have an acyclic orientation of the full graph G bar. This says B comes before D and A comes before C. If I multiply by D, it just flips the edge. So multiplying is just edge flipping. Before B was before D, but now I like D better than D, so now D comes before B and it corresponds to this orientation. If I now multiply by C, I flip that over. So both multiplication is a very nice combinatorial meaning, and there's an obvious random walk on these graphs that you can analyze via the algebra of left regular beta. This was done by Athanasiadis and Diaconis, 2010. They use a slightly different LRB, but the same techniques. Okay, and the last example is sort of a universal example. I'm going to look at a semilattice. A semilattice here will be a meet semilattice. And so I have every pair of elements in the poset has a greatest lower bound. Greatest lower bound. If I say that that gives me a product, x times y is the GLB of x and y, that's a commutative and associative and idempotent operation, so I have a commutative semigroup. And conversely, if I have a commutative idempotent semigroup, there's a natural way to consider it as a partially ordered set with a meet. Just think of how you do just think of sets under intersection. I won't get into the details, but at any rate, if I look at flags in a semilattice, or lattice, looking at descending flags, they have a natural product. Namely, I have two chains, flags. I use the bottom element xk and then multiply through all the elements in the second chain of y's. Well, that drops them, but because this multiplication is not 1 to 1, I could get some equalities. Maybe xk y1 is equal to xk y2 is equal to xk y3 is strictly greater than xk y2. And if I just wipe out the equalities, it's not too hard to see that that's a associative operation on the set of chains. And now it's clearly idempotent. The y's are just the x's. Well, seen all. Because xk x1 is less than or equal to, it's a GCD of xk and x1, but xk is less than x1. It's idempotent. Right? Now, if I multiply this by the x's at the end again, well, I've seen all the x's. I don't need to multiply by the x's. Again, they're above them. So here's a left regular band. This is called the Rhodes expansion. One-sided, you can obviously have a dual idea. It's an LRB. It's a left regular band. Okay? Not too hard to show, but it's kind of a multiplication that it sort of shows up in the butterfly level. It's kind of multiplication on chains. The R order is the right order on the, I'm using semigroup language here, but R order is the semigroup order on right ideals. For instance, like we did in couple of slides ago. Its Hasse diagram is a tree. There's something free about this. And the order on left principal ideals is exactly the Hasse diagram of the semi-lattice lambda. Okay. So here, if I start with the free semi-lattice and apply this idea, I actually get the free left regular band, because a word, a non-repeating word can be associated with a chain in the subset lattice. And I just record 3, 1, 2, 4, 5. I just record a chain of the subsets which arise. Right? 3 came first, and they added 1, and they added 2. And so this is a natural generalization of Okay, so here is the free semi-lattice, free left regular band on 3 generators, and here is principal right ideals. It's a tree. I'm just ordering non-repeating words by prefix orders, just like the prefix order on the free model. And we're gonna, in order to understand more of the representation theory, I have to look at certain subintervals of this graph. So I look at a semi-open interval. This is, down here is everybody equal to this left ideal. B is up there, and I look at everybody in the blue circles, everything in the semi-open interval. Why is that important? Because it gives us a way, now I'm getting deeper into the representation theory, these X to N spaces are what you study in the homology of algebras. Sx and Sy are 2 simple modules of the left regular band algebra. They're indexed by elements of this lattice. And so here is our one of the main theorems. Okay. And that's why this semi-open interval is important. I look at the lattice. I look at the set of chains in this coset. Okay, it's a simplicial complex, so it's a topological space. I look at its reduced homology, and that gives me this X to N space. Okay, that's what's important here is that usually these X spaces are highly algebraic and hard to compute. But in this case, they have a natural poset theoretic topological meaning, which you can gather from the space itself. Okay, so here's the difference between left and right in the just compare in the free left regular band on three generators. Here's the right principal ideal order, okay? And there's the left principal ideal order. Subset, it's a subset of everything. And in general, if I looked at a hyperplane monoid, the left idea, the left principal, the left order is exactly the intersection lattice in the sense of hyperplane arrangement theory, and the right order is exactly the face poset. So if you're studying hyperplane arrangements, page 7, you're going to define the intersection lattice, and on page 9, the face lattice, the face poset, and they turn out to be naturally associated to this model. The connection between them is what's important. Okay.
A few minutes, if you like to leave a few minutes, Professor.
Okay.
3 minutes or so.
Okay. So let me just get to the, I'll just get to the computation of the quiver of this algebra. The quiver is one of the important invariants of a finite dimensional algebra. Okay. Okay, so quivers are important because they give us a way to compute the all basic algebras. So I don't want to spend too much time on that, but here's the corollary. The arrows in the quiver, the graph of the quiver has as vertices the simple modules of the algebra, and the edges are the dimension of the first X space. But the first X space is the reduced zero homology of this poset. Well, what's the zero homology of a simplicial complex? Just counting connected components. So you get this wonderful way to compute this dimension of this x1. It's just a number of connected components in this simplicial complex minus 1 because we have to reduce them. So at least I'll show you how to compute it. And you basically can compute it by hand in computing the quiver of say this free left regular band of 3 generators. Okay, so the theorem says this. Here are the simple modules, and 8 simple modules. Suppose I want to know what's the dimension of the x space? How many edges in the quiver between the red guy on the bottom and the blue guy on top? So I come back, I pull it back from the left to the right. B is on top, BAC is on the bottom, and then I erase the top because it's a semi-open integral. And I ask you how many connected components you have. There's 2. And then the theorem says, well, that means there's 1 edge. That means the dimension of the x space between that simple module and that simple module is 1. So you can see it. So here's another example. From the bottom to the top, I erase the top. There are 3 connected components, so there are 2 edges. The dimension of this x space from the bottom to the top is 2. If I stick these guys next to each other, well, there's 1 connected component. I subtract 1, so there's no edges between the bottom to the guy just above it. And you can compute the quiver that way, almost by hand for any reasonable size left regular band from this theorem. So how much? Okay, I'll just say something about global dimensions. I just wanted to say this theorem because it's an interesting connection here, which I don't really understand. It's just we sort of bumped into it. You have to know a little bit about global dimension. We'll take that definition. I look at all these spaces. The last time I see a non-zero cohomology of one of these order complexes, that number n is the global dimension of the algebra in the sense of finite algebra, of associative algebra. Well, then you just look at something more familiar, I guess, to algebraic combinatorics, the little ray number of a simplicial complex. And you notice that there's a connection between just the definitions. And so you immediately get this nice result that the global dimension of the algebra left regular band is less than or equal to the Lorraine number of the order complex of the underlying poset. And then you can see that if the Hasse diagram of the poset is a tree, then the global dimension is at most 1. And that means that the algebra has a nice algebraic property called heredity. Submodules of projected models are projected. This started with Ken Brown, who did a heavy computation to prove this, but topologically it just falls out of the fact that the poset of free left regular band is a tree. And here's some fact that you can prove that is sort of mysterious to me in the present. So it says that if you take a graph, and you take its partially commutative left regular band, then you get equality between the global dimension of that algebra and the Lorraine number of the clique complex of the graph. The clique complex is the graph on the vertices of the simplicial complex on the vertices of the graph, whose faces are the complete subgraphs, the cliques. That's the next, so that's a flag complex, and you get equality. So here you have a natural interpretation of the Lorraine number as a global dimension of a non-commutative algebra. Now, is that by accident or interesting? Somebody else to say. And then I'll close, well, I'll skip all the stuff on CW. As you can read it. Oh, here. Okay, so we submitted this thing in 2015. We wrote a lot of letters to the AMS that said, don't worry. And then in 2018, they said they're sorry, the editor never sent it out for referee, and he's no longer an editor. It was accepted in 2019, and it's about to appear. So you can read what I talked about and more there. Oh, the AMS said, oh, by the way, we just take your document. We don't even do any editing on your document. It's just published. And then charge people $85, but I'm going to give it to you for free. Yes. Okay. Another great book to read is Ben Steinberg's book on representation theory of monolites. Okay, so I hope you get a little taste that monolites are not as strange as the finite monolites are not as strange as they seem. And then there's two more books that came out in the last year by Edward and Jim, Topics in Hyperplane Arrangements, which has this kind of stuff and generalizations. And then another book that I haven't looked at yet called Bind Monolites for Hyperplane Arrangements. They extend the theory even further, different kinds of monolites. So I just gave you 1,500 pages to read on this stuff. So people take it seriously, yes. And thank you for your attention.
Okay, thank you very much, Stuart. We have time for one or two short questions. Question for the audience. Any question only you can ask because I'm not sure if you can hear me. Ask me, Stuart, if you have any question. Questions?
If we have the free error be associated to a graph, right? And then the partially commuted.
Yeah.
So can two non-isomorphic graphs give the same setting, the same error be, or
It'll be different.
It will always be different?
Yeah. Okay. Oh, is Ron here? Good. I wrote in big letters at the end, Ron and Yuval. I wanted to save my remarks for the end so that most people know that it was a belated birthday party for Ron and Yuval. So Ron and Yuval are some of my dearest friends, and I lived in their neighborhood literally. For 25 years, Yuval's office was right across the corridor from mine until he moved up a little bit. He moved up in the world where he was up. Ron's office was next door. And one of the better days to come to Bar Ilan was when I'd walk towards my office, turn to the left and see that Yuval and Ron were sitting in their offices. So I sort of moved into this kind of algebraic combinatorics in the last 15 years, and I was lucky to have Ron and Yuval right next door. So I learned a lot. And they were very kind to me. They asked me to talk in their wonderful seminar a lot. They're great personal friends and amazing mathematicians, and now I'm going to make them work on these products of groups and monolites and tell them about the representation theory of the characters. But, it's been a pleasure.
Okay, thank you very much.